So we'll get through a few sections of chapter 7 today, then one more section on Monday, and that'll be the end. Okay. All right. So last time talking about the maximum principle, that a solution of a harmonic function assumes its maximum on the and minimum on the boundary. So here's some uses of that to learn other things about harmonic functions. Okay. Yeah. Of the maximum principle. Okay. So first is the Dirichlet problem. Which is Laplacian of u equals f on the domain D, and u is equal to some function g on the boundary of D. As a unique solution. Now, there are a lot of results I'm going to show today that deal with uniqueness. The way you prove uniqueness is you assume you have two solutions and show that the difference of them must be 0. And so you're going to see this technique over and over and over again. So that makes for some very nice, elegant, quick proofs. So let's assume that I have two solutions of this Dirichlet problem. And I let V equal their difference. So what that means is, by linearity, Laplacian of V is 0, and U is equal to 0 on the boundary. But, so not U, V. But V must assume its maximum and minimum on the boundary. So that means that V must be greater or equal to 0, a minimum, and less than or equal to 0. So it's constrained on both sides by 0 within the domain, so that V is identically equal to 0 in D. So U1 equals U2, and the solution is unique. All right. So any questions about how that was done? So right here is where we use the maximum principle. That maximum must be assumed on the boundary. Okay. Now, let's see. A related result, because in this case, I assume that U1 and U2 are solutions of the exact same Dirichlet problem with the exact same boundary data. U is equal to G. So this is used to prove uniqueness. But we also have another result. You can think of it as like stability of solutions or well-posedness. What if U1 and U2 satisfied Dirichlet problems with different boundary data? So we could use the maximum principle for that too. Okay. So the next result, let's suppose that U1 is a solution of this Poisson's equation, and U2 solves the same Poisson's equation. However, the boundary data are different. So U1 is equal to G1, U2 is equal to G2 on the boundary. Then we could say that the maximum in the interior of a difference of solutions is less or equal to the maximum over the boundary of difference in your boundary data. And that is just as easily proven because we've defined V to be U1 minus u2, so that means that Laplacian of v is 0, and v is equal to g1 minus g2 on the boundary. And again, maximum minimum must be assumed on the boundary, so that means that v is constrained by the absolute value of a difference in the interior. And that's it. That's the proof. Okay. So, sorry. I need to say the maximum of this difference on the boundary.
What are we proving here? I'm sorry.
What?
What are we proving?
That.
Oh, okay.
Yeah. Zero. Proof.
Yeah.
Okay. Okay. All right. I know, but the proofs are so easy, but it's flying by. Okay. Yeah, and then the v is u1 minus u2, which gives you this. So, so the thing is, we don't know from this whether the maximum or minimum has the larger absolute value, but we just use it. But we just use absolute value here and take the largest of those, just to have all our bases covered. So, what I'm saying is, it's possible that we can find a sharper upper or lower bound for v, but this bound definitely works. So in other words, if you think in terms of like numerical solutions, a small change or small error in the boundary data does not lead to a large error in your solution. So that's something that's helpful to know. Okay. Now, okay, so that's a couple of applications of the maximum principle, and in fact, that finishes section 7.4 right there. It's a very short section. The next section is not much longer. There are some helpful identities related to harmonic functions, and gradients, and Laplacians, and so forth, that are useful in proving other results that we'll get to in a bit. And these identities are useful for many different manipulations involving PDEs to help prove various things, especially, or derive new forms of equations or make other manipulations. So these are just good to know manipulations. Oh yes, gotta move the computer. Okay. All right, and so there's a collection of pre-identities that anyone studying PDE should know. It's kind of weird that we're getting to them at the end of the semester, but whatever. It's called Green's identities. Okay. Now, before I get into the identities themselves, there's one very important theorem that actually is covered in multivariable calculus, like Math 280, that I should remind you of. That's the divergence theorem, also known as Gauss divergence theorem, that says that the integral over the interior of a domain of the divergence of a function is equal to the integral over the boundary of your domain of the normal component of your function that you're taking a divergence of. And this could be useful both ways. You might have an integral over the boundary of some normal component, and then you could take the integral over the interior of a divergence, and maybe that integral is simpler. Or if you have a way around. So whatever it is you need to do. So you can actually use this divergence theorem by choosing psi in different ways to arrive at the Green's identities. Now, Green's name has come up as another important theorem for vector calculus, Green's theorem, which you can think of actually as a special case of a divergence theorem. So our first Green's identity, we just let psi equal, okay, I should mention psi is, okay, psi actually has to be a vector field for this to make sense. So if I choose psi equal to the gradient of u for some function u, then the integral of divergence of gradients of u, but that's just a Laplacian. That is equal to the gradient taking the normal components over the boundary, but that is just the normal derivative. Okay, so the integral of the Laplacian over the interior is equal to the integral of the normal derivative over a boundary. Now, like for Neumann problems, we're specifying the normal derivative on the boundary. So that could be, so this identity can be very convenient for that. In fact, it's because of this identity that we had the compatibility condition for a Neumann problem. Okay. The next Green's identity. Okay. Actually, what I have written in the notes third, I'm going to do second. I think a presentation actually makes more sense that way. Not yours, on the book. All right, let psi equal to v gradient of u. Okay. So what you get by just by filling this in, we have divergence of v gradient u dx dy. And then plugging this in over here, we have, this is over the interior, it's equal to the integral over the boundary of v, and I take the normal component of this, so this is going to give me v times the normal derivative of u. Okay. Now, here's where I'm not going to cover everything, because this is not the actual second Green's identity. I need to do one more step. But I'm not going to show you how to do the step because it's one of the homework problems. So it won't be bad. It's basically Cal 1 stuff. Well, okay, Cal 1 multivariable setting. Okay. So it turns out that I'm going to modify this. So the second Green's identity is that the integral over the boundary of v times the normal derivative of u turns out to be equal to integral over the interior of v Laplacian of u plus gradient of u dot product with gradient of v. Okay. Now, how you would go about showing this in product law, of course, the definitions of all these operations, divergence, gradient, and so forth. Actually, at least the stuff we were talking about on Monday, like some of the relations I was doing, this is basically that sort of thing.
That sort of thing.
Yeah, so I think proving this will give you an idea of how these things work.
Yeah, I already decided I'm doing homework 7.
Oh, okay, good call. All right. So which one are you not doing?
I don't know yet.
Okay. All right, so that is the second Green's identity, which I've not fully proven. But from this, it becomes very easy to get the third Green's identity. So you can think of it as a consequence of this. Okay. Okay, so third Green's identity, I let psi equal to v gradient of u, again, minus u gradient of v. Right. So what I can do is apply the second Green's identity twice. So I have integral over boundary of v normal derivative of u minus u normal derivative of v ds equals, and then I'll be integral over the interior of what I had before, v Laplacian of u plus gradient of u dot gradient of v minus what I would get from second Green's identity for this expression. You just switch u and v. U Laplacian of v minus gradient of v dot gradient of u. But the dot product for real valued functions is commutative. So these terms cancel out. So you just get v Laplacian of u minus u Laplacian of v. Okay. And so these Green's identities make it very convenient to go back and forth between normal derivatives on the boundary and Laplacians on the interior. And so dealing with Laplacian and normal derivatives in these various problems we're considering, it's quite nice to have. But the way I'm going to use these Green's identities now is, okay. Is for prove some uniqueness results. All right, so what we have is, okay, it's kind of weird because I feel like this one is something I proved already. And therefore, why should I prove it again? But let me confirm this beyond a shadow of a doubt. Okay, because in the last section I proved, okay, yeah, Dirichlet problem has at most one solution. And then, yeah, okay, I don't know what they're thinking, but yeah, so first part of the theorem is Dirichlet problem. Laplacian equals f, u equals g on the boundary. Has the most one solution, but we've already covered it. Use the maximum principle on the difference between two solutions. So, but I guess the reason why the textbook presented it this way is now we have uniqueness results for other problems. So if alpha is non-negative constant, then the Robin problem, Laplacian is equal to f in the domain, and we have u plus alpha normal derivative of u equals g on the boundary of the domain. Also has at most one solution. All right, so we have uniqueness for that problem as well. And finally, let's not leave out Neumann boundary conditions. The Neumann problem so we have Laplacian equals f, and the normal derivative of u is equal to g on the boundary of d. We do not have uniqueness in this case, but what we can say is any two solutions differ by a constant. Okay, so we have a weaker form of uniqueness in that case.
Linear combination.
What?
Like differ by a constant.
Oh,
no, not a linear combination, but they differ by a constant.
Yeah. Yeah. So in other words, their derivatives must be equal. Yes. Yes. So the derivatives of a solution of a Neumann problem are unique. Okay. All right. So now I can use, well, it turns out we have 3 Green's identities. So I'm not going to bother proving number 1, because I already did. So number 2 and 3, we can actually use this third Green's identity to prove both of these. All right, so first, for the Neumann problem, for Robin problem, we'll do that first. Okay. Okay, so first one already done. Second one, we have, so I'm going to let v equal u1 minus u2 again. So what that means is the Laplacian of v is 0. And for boundary conditions, we have v plus alpha normal derivative of v is 0. So homogeneous all the way around. Okay. In fact, okay, yeah, this is very good. So Green's identity, number 3 says that the integral over a boundary of v, partial derivative of v with respect to the normal derivative. Now normal is equal to v Laplacian of v, but that's 0. So we just have the integral over interior of dot product of gradient of v with itself. Okay. Now, from a boundary condition, I can say that v here is equal to minus alpha normal derivative of v. So I can go ahead and substitute that into that integral. And what we get is minus alpha integral over boundary of normal derivative of v squared ds. So this integral is definitely going to be less than or equal to 0 because alpha is given to be non-negative, so that's going to be important here.
The line before that, the second one you mean in the interior, right?
Ah, dang it, yes, interior. Okay, equal to the integral over the interior. And this is going to be the norm of gradient of v squared. So, so this is going to be greater than or equal to 0. So both integrals must be equal to 0. Okay. Now, okay. Okay, so then what happens here is, okay. So this tells us from this, okay. So because of this, we have both being equal to 0. Okay. And then we have integral over interior of the norm. Okay, so so that tells us that the gradient is equal to 0 throughout the entire domain, but it also tells us from here that the normal derivative is 0 on the boundary. So if we go back to the boundary condition, what else can we conclude? What else is equal to 0?
V.
Yeah, v is 0 on the boundary therefore, v must be 0 in the interior. Why?
Because that's the
Maximum principal. Okay. All right. So that takes care of that. So therefore, U1 equals U2, the solution is unique. Okay. Last part, the Neumann problem, same thing. V is equal to U1 minus U2, and we go through, and now what we have is Laplacian of V is 0, and normal derivative is equal to 0 on the boundary. And as we apply the same identity, we have the same thing, except the same integrals at the start, except this one is definitely going to be 0 because of a boundary condition. And now we're left with this. So we have integral over the interior. So this is third identity again, that the norm of v gradient of v squared is 0, which tells you that the gradient of v is 0 throughout the entire domain. That means all partial derivatives of v are 0. So if all the derivatives are 0, then what do we know about the function? It has to be a constant. On the entire domain D, so that means that the U1 minus U2, the difference of two solutions, has to be a constant. Okay. All right, so the manipulations are basically the same as this, except I'm not doing this here, because this integral is really equal to the integral over the boundary of v times the normal derivative. But because of the boundary condition we have here, that has to be 0. So that's why all of that fell into place. Okay, so questions about how these were proven? All right, and that's the end of that section. Okay, although the next section is a little more substantial. So in fact, we're going to go back for this section to time-dependent problems, because we have a maximum principle for the Laplace's equation and Poisson's equation. It turns out we can also have a maximum principle for the heat equation. Using very similar ideas. Okay. Okay, so the problem we're going to look at, that du dt is equal to k Laplacian of u in some domain. Now, the discussion will be like for a three-dimensional domain, although if I stick to 2 dimensions, it'll be easier to visualize what this domain looks like we're dealing with. In fact, there's nothing in here. Yeah, there's nothing in here but it's intrinsically 3D. So I'm going to knock it down to 2 dimensions just for visualization's sake. Okay. Now, I can define a domain Q sub t. Set of all points in space, which could be however many dimensions you have, including t as a time variable, where your spatial variables are in your domain D, whatever that is, and t is between 0 and you're restricting yourself to a final time, capital T. and then the boundary, and let's find, oh, this domain has a boundary in space and time, but I'm also going to define this boundary sub P of Qt. And this consists of the domain D, Cartesian product with t equals 0, and we combine that with the boundary of D, Cartesian product with the time interval 0 to t. Okay, now all of this needs some explaining, and I'm going to use a picture to help. So if I have so three-dimensional space, but we have two spatial dimensions and one time dimension. That's why I'm knocking it down to 2D, so I can draw all this stuff. So here you have your spatial domain sitting in the xy plane. This is D. Then we build on top of that in time direction, starting from the xy plane, which is t equals 0, up to t equals capital T. So this entire domain, everything, is q sub t. So it consists of all points x, y in your domain, and all time values between 0 and capital T. Now, as far as this boundary sub p here, I'm not really sure what else to call it, but I don't know if the book has a different term for it, because it is not the entire boundary. Okay, there's a term for it. This is called the parabolic boundary. Not sure why we call it that, but okay. So a parabolic boundary consists of, okay, this first piece is the domain D sitting in this plane, okay. Then the second part is the boundary of D all the way from here to here. So it's the sides. The top is excluded. So this part is part of the overall boundary of Qt. It is not part of the parabolic boundary. So in other words, so you're taking the lid off. Okay. Okay. And everything else in the boundary of Q sub t is in the parabolic boundary. Okay.
Maybe they call it parabolic because it's the first derivative of t.
Maybe. Yeah,
Hyperbolic
because
is
the
like
parabolic problem, maybe.
Yeah.
I don't know. Okay. Now, more notation, unfortunately. I'm going to define the set C sub h consists of a set of all functions that are twice differentiable with respect to your spatial variables, x, y, or x, y, z. Once differentiable with respect to t, and it must be continuous in the closure of Qt. So that's Qt itself union the entire boundary, not just the parabolic boundary. Okay, so this set C sub h consists of whatever functions are eligible to be solutions of a heat equation in this domain. Now, basically, they possess the required number of derivatives and the required continuity. Okay. Now, okay, so the ultimate goal here is to prove that this problem, the heat equation with appropriate initial and boundary conditions has a unique solution. And for that, we'd like to proceed in a similar way as with Laplace's or Poisson's equation and have some sort of maximum principle. But in order to get uniqueness, we need to prove some preliminary results first. Okay. Okay. So. What's kind of sad is, as long as I've been a mathematician, I've never really understood why some results are called theorems and some are called propositions. I should look that up. I mean, other things like lemma or corollary, I understand their purposes. Like a lemma is used to set up a theorem usually. It's like a less important result that helps. And corollary is something like an immediate consequence of a theorem. But theorem versus propositions, like, what? So.
We should propose this first and then it's sort of.
Maybe?
Maybe it's level of importance, but I'm Googling it right now.
That's my guess, that theorems, of course, being most important. I've never actually bothered to prove a proposition in any of my papers. I would never call it a proposition. So, okay, yes, enlighten us all. Okay. All right.
Proposition of proved and often interesting result, but generally less important than theorem.
Okay.
Okay.
All right. That's good. Well, which is kind of funny because I think this is, we really need this proposition to prove something else that is called a theorem. So, okay. All right. So, so first, let's suppose we have a function in this function space, and satisfies vt minus k Laplacian of v is not equal to 0, so it's not a solution of a heat equation. It is negative on this domain. Then we can say that V has no local maximum in the interior of Qt. And V has its maximum on the parabolic boundary of Qt. Okay. All right, so now go ahead and prove this by contradiction. So let V have a local max in Qt. Now one thing that's very important to point out to avoid getting too confused, this is a weird kind of maximum because it's with respect, we normally think of a maximum minimum as being with respect to spatial variables, or maybe if you only have one time variable, so it's a one-dimensional max-min problem. Here we're taking maximum over space and time. So we have our solution, or function v, defined on D, but it is also evolving over time, and we're taking the maximum over all those values. So what that means is, okay, I'm going to say, instead of saying local maximum in here, I'm going to identify the specific point. So at this point Q, in Qt, we assume that V has a local maximum there. Then what do we know? To have a local maximum, what has to be true of your derivatives? Calculus 1, people. At a maximum, what's true of your derivatives? Zero. You remember from Calc 1, take the derivative, set it equal to 0. And what, okay, that's first derivative. What about second derivative?
It,
Will concave
If
down,
it's-
right?
Yes, therefore second derivative is
positive?
Negative.
negative.
Negative, yeah.
Yeah, so positive for a min, negative for a max. Okay, so this tells us that the gradient of V is 0. Also, because it's maximum in space-time, dv dt is 0 at Q. Also, Now, okay, you answer these questions for one variable case. Multivariable case, your gradient is 0, and instead of a second derivative being negative, the Hessian is negative definite. But for a matrix to be negative definite, all the diagonal entries must be negative. Therefore, the Laplacian of V must be negative. Now, K is a positive constant, so Vt minus K Laplacian of V. So this is also true at the point Q. Well, that's going to be positive, because this is 0. We have negative times a negative gives us a positive. So that's a contradiction. Okay. All right. So a local maximum is not possible. Okay. Now, a continuous function on a compact set has a maximum and a minimum. So, because V is continuous, that's one of the assumptions of being in this function space. Continuous on the closure of Qt, so that means that V has a maximum somewhere in this domain, either the interior or the boundary. Well, we just ruled out the interior, so it has to be on the boundary. But the thing is, I'm trying to prove, okay, so I've proven this. I'm still working on this. I want the max to be on the parabolic boundary. But all I know right now is it's on the boundary. So what do I have to, what's left? What do I still have to show? Or like, what do I have to rule out? What's the difference between the boundary and the parabolic boundary? The picture's over there.
Oh.
The lid.
The lid. So I have to make sure that wherever this maximum is, it cannot be on the lid. Okay. So if V's maximum at the point Q is in the lid, which is the domain D, Cartesian product with T equal capital T, then dV dt at this point must be greater or equal to 0. The reason why is, okay, so you're at the top of this domain in time. The maximum is here. So the function v must be increasing in time. So surely it can't be decreasing to hit a maximum. So it must be at least greater than or equal to 0. Okay. Also, v is a local maximum in space. So if we just consider a spatial domain, D, is a local max there, which says that, once again, the Laplacian of V is negative, or at Q. So if we put those two things together, we have dV dt, which is non-negative, and then minus k Laplacian of V, which is now positive, is going to be positive. But again, that's a contradiction. So it's negative. It's positive at Q. But the thing is also positive near Q. And in other words, spilling into the domain. So if a function is positive at a point, by continuity, it is also positive in a neighborhood of that point. So that means there are certain points within Qt, like in the interior, where this quantity is still positive. So that also is a contradiction. All right. So that means that the maximum cannot be on the lid, it must be elsewhere on the boundary, so within the parabolic boundary, and we're done. Okay. So all of this came about from thinking about what signs should your derivative have if you're at a local maximum. So keeping those in mind made everything fall into place. Any questions about that? All right. Because the fact is, the lid, the maximum t value is important. Suppose we have a maximum when on the bottom part, where t equals 0. If a maximum occurs there, that means as t increases, then dv dt is negative because it's decreasing in that case. So where you're at in time is important to take into account, what are the actual derivatives, like are they positive or negative. Okay. All right, so there goes our proposition. And now we can use this in what time we have left to prove a few other things. Well, I have two theorems and a corollary. So this is a very productive proposition.
So Dr. Members?
Yeah.
Is the opposite true, like if Vt minus k, the plus and v were greater than 0, so v has no local main, and v has its main on?
We'll see. That would certainly, okay, so certainly we could have no local min. And then, okay, so now suppose the min, I think that would be used to rule out a minimum at t equals 0.
T equals 0.
Yeah. So, okay. All right. Okay. So now for the first theorem that follows from this. Okay. So let's suppose that u in this function space is a solution of a heat equation. Okay. That's a strange delta in this domain qt. Then u achieves its maximum and minimum values. Oh, interesting. On the parabolic boundary. Okay, so going back to a proposition. Oh, okay. Now, what I'm actually going to do here is prove it for the maximum case, and then the minimum case is similar. But one thing I want to check. Okay. Because if you, the reason why you only have to prove it from a maximum is that if u is the solution of a heat equation, and you prove that the maximum is in the parabolic boundary, then minus u is also a solution of a heat equation. And so you maximize minus u, which is the same as minimizing u. But yeah, going back to the proposition here, if Vt is positive, if this expression is positive and there's no local min, okay, so in this case, if there's a minimum at the lid, then it is decreasing there, so Vt is negative, and the Laplacian is positive. So all expression is negative. Actually, yeah, okay, I correct what I said earlier. The lid is ruled out either way. so depending on whether this is negative or positive.
Right.
Yeah.
Not that the bottom part is.
Right. Yeah. Yes, it's always the lid. Okay. Okay. This is what I get for trying to do things in my head. So yeah, there's if there's a minimum here, you have this decreasing. Dt is less than 0. Laplacian being at a min is positive, so Vt minus k Laplacian of v. So that is negative is negative, but we are assuming that this is positive. And the reason why it has to work always with the lid rather than t equals 0 is because the sign of a derivative, positive or negative, is whether a function is increasing or decreasing as t is increasing.
T is increasing, right.
Yeah. So, okay. So the proposition says that Vt minus k Laplacian is positive. The minimum is on the parabolic boundary. Okay. So now we're going to focus on proving that the maximum is on the parabolic boundary, and then you can work with minus u to show that the min is on the parabolic boundary. Okay, how am I doing
Did we already show that?
that? But that's Vt minus k Laplacian less than 0.
This will be equal, or this is
Equal.
equal to 0.
Yeah.
Okay.
Okay. But for this, we're going to fall back on that proposition. I can let v equal u minus epsilon t. So then I can say that Vt minus k Laplacian v, which is ut minus k Laplacian of u, minus d dt of this plus Laplacian of epsilon t. Now, u is a solution, so this is 0. Laplacian is spatial derivative, so that's 0. And the derivative of t with respect to t, of course, is 1. So this whole thing is equal to wait. Why do I have? Oh, okay, I have a typo in the notes, but I have an extra factor of k in there for some reason. Okay, so it's equal to minus epsilon, because we're assuming that epsilon is positive. Okay, so Vt minus k Laplacian v is negative, therefore the proposition applies to v. So that means that the maximum of v on Qt is on a parabolic boundary by the proposition. Okay. Also, we can say that the maximum on the parabolic boundary is less than or equal to m, which I define as the maximum on the parabolic boundary of u. And the reason for that is v is definitely less than or equal to u, because we're subtracting something off. So whatever maximum u has on the parabolic boundary, that has to be an upper bound for whatever maximum v is. Okay, so that tells me that u is bounded by m plus epsilon capital T, because v is equal to u minus epsilon t, so I'm just moving that to the other side, basically, to get upper bound on u. So let epsilon go to 0. Okay, so that gives us that U is less than or equal to capital M. But since M is the maximum on the parabolic boundary, that's where the maximum of U, so I should say the maximum over the whole domain of U must occur on the parabolic boundary. Okay, so because we've already defined capital M to be the maximum on that parabolic boundary, but if U is, because these statements I've made here apply on the whole domain. Okay. Because keep in mind, because of what is whatever proposition, the maximum of V on the whole domain, which has to be equal to the maximum on the parabolic boundary, is less than or equal to M. But V is equal to U minus epsilon T. So from this relationship, U minus epsilon T is less than or equal to M. Okay. So I'm just filling in a few more steps here. Sorry, I should have been more clear up front. Okay. So a proposition that I proved earlier states that maximum V is on the parabolic boundary. Therefore, the maximum V on the whole domain, which is equal to maximum parabolic boundary, is less than or equal to M, which is the maximum of U on the parabolic boundary, just because V is less than or equal to U. Everywhere. But because of how V is defined, I have this relationship now on the whole domain. Rearrange. So U is bounded by this. Let epsilon go to 0, and I get U is less than or equal to M. Not just in the parabolic boundary where I defined it, but on the entire domain. Okay. And because of where M is obtained, it's the maximum on the parabolic boundary, that's where the maximum of U has to occur. Please tell me it makes some sense.
It'll make sense when I do the homework.
Okay. All right. Well, because even when the manipulations are simple, you have to take time to convince yourself. All right. But now you have all the breadcrumbs. I'm sorry I didn't write them out this much earlier. Okay. Now, since the maximum and, in fact, the minimum also had to occur on the parabolic boundary, I have this result about that follows from this one, about the stability of solutions. Okay, so let's suppose U1 and U2 are solutions of the heat equation. The same, actually, not necessarily a homogeneous heat equation, so we can have a heat source. Okay. Oh, got some typos there to fix. And let's suppose they have different initial conditions. So U1 is at time 0 is equal to F1. U2 is is equal to F2. Okay. And then we have boundary, so this is the initial conditions. The boundary conditions will make them Dirichlet. So U1 is equal to H1, and U2 is equal to H2. And this is for X and Y on the boundary of D, and T between 0 and capital T. So what we get then is, on the entire domain, the difference between U1 and U2 is bounded by the maximum over the spatial domain of the initial data difference, plus the maximum over the boundary of your spatial domain, Cartesian product of a time domain, of the difference between your boundary conditions. Okay, so basically this is about stability of solutions. So a small change in the initial data or for boundary data leads to a small change in the solution. That's the important thing to gather from here. To prove this, well, we have V equals U1 minus U2, like so many times before. So that means that V solves the homogeneous heat equation. And, bless you, V initial data is F1 minus F2, and the boundary data is H1 bless you, minus H2. This is boundary. Okay. I want to check here about the stability. Okay. So we can use the same theorem as before because for the preceding theorem, V has its maximum and minimum on the parabolic boundary of Qt, but where's the difference of solutions? What is this difference of solutions equal to on the boundary? It's equal to this, so this is the difference when t equals 0, and this is the difference when x, y, t are on the boundary. So one of these differences is going to be the maximum possible difference on the boundary, and you can just add them together to be on the safe side. So in fact, I didn't even have to add these together. I could have just taken the maximum of them, and that would have worked too. So really, that's the end of it right here. That because V's max and min have to be on the boundary, then U1 minus U2 must be, its absolute value must be bounded by the maximum. So I can actually prove a strong result in this. I have the maximum of the max difference in the initial data, or the max difference in the boundary data. Because one of these is going to be the maximum on the entire parabolic boundary, and that is the max absolute value of V. Okay. Any questions about that? Now, one very important consequence that comes from this is if I let F1 equal F2, V1 equal V2, H1 equal H2, what does it say about the difference u1 minus u2
Zero.
has to be 0. So u1 minus u2 is less than or equal to 0. Therefore, must equal 0. Therefore, uniqueness. Okay. So we have stability and uniqueness of solutions all in one shot. Okay. Alrighty. Now, this was for a multi-dimensional heat equation. Oh man. Okay. I just have a couple more results. Maybe Dr. Ding can tell fewer stories today.
I don't think it's here though.
Oh, that would be weird.
He'll be here.
Huh?
He leaves. Like he went his own class.
Not the 12 o'clock over there,
I've seen him walk that.
3 o'clock.
Okay, so I have a corollary. This is for a 1D heat equation. So suppose I have a solution and I can, it is one dimension, so I can express it in the usual format you're accustomed to.
Yeah.
Some separation of variables land. Okay. So this solves the heat equation,
Dirichlet boundary.
and then yeah, Dirichlet boundary conditions. And then we have this data f of x on the interval 0 to L. And the theorem says, or corollary says that if this series for f of x the usual Fourier sine series converges uniformly, so something dealing with analysis. So I think Dr. Ding would appreciate this. To f of x on the interval 0L, then this series for u, which I'll label star, does the same, converges uniformly on the space-time domain. So 0L, 0 to capital T, and U is a classical solution. So in other words, it has all of the required derivatives. Okay. Now, all right. So to quickly prove this.
F of x equals that converges uniformly to f of x.
What?
So if f of x equals that converges.
If that series converges uniformly to f of x. I mean, okay, I'm being sloppy. Just okay. There.
Alright, yeah.
Okay. Will that prevent you from having connection?
But yeah.
Okay. All right. Nothing. Okay, I may have to let a proposition wait till Monday.
Did you ever say why that snake was there?
Let's try what?
It was already there before the class,
Okay.
before the numerical.
Okay.
Okay. So, all right. So, because of the uniform convergence, and it's something you should know from Dr. Ding's class. So what we get is, for any epsilon, there exists n epsilon, such that okay. So we actually have, this is big, it deals with Cauchy sequences actually. And we are dealing with this as a complete space. So So Cauchy sequences converge. Oh, that's 771 stuff. Sorry. Okay, maybe Amber S would appreciate this more than you guys.
What we did.
So you do need uniform convergence, yeah. Okay, so because this is partial sum L minus partial sum K minus 1. Now this is a classical solution of the heat equation. Satisfies the boundary conditions, satisfies the PDE, and oh, sorry, I should not have written that. Okay, that comes later. So we have this from a definition of uniform convergence. Now, if I throw in the exponential factors, that is a classical solution of the heat equation. It satisfies the boundary conditions, satisfies the PDE. It is a finite sum, so it definitely satisfies whatever initial condition is just comes. It's this initial data. So we have a maximum principle applies, and therefore it is bounded by epsilon. Okay, because this is a value on the boundary, the parabolic boundary, initial data. So that serves as a bound on the whole solution. And what that means is this series star converges uniformly. And because of uniform convergence, to check whether it satisfies the PDE, you can swap summation and differentiation. So you can confirm directly is a classical solution by checking the PDE, boundary conditions, initial condition. Okay. All right. So I won't. Okay, I'm 1 minute past time. So there is one more proposition about a maximum principle for a Neumann problem. I'll just do that first thing on Monday and cover the section I had in mind for that. And I think we can finish. That's what I'm hoping for.
Well, we don't have real analysis, so we can go a little bit to finish.
I'll keep that in mind, but I'll still try not to.
So
Yeah.
there's a chance we may not have any class on Wednesday.
Right. We'll see. Okay. All right.